Welcome back. Today we've got a little project. It's a feasibility model thing, basically just to show if it works or not. It's essentially a test rig. We got a device to be tested, which is this end. It's not that because I can't show the real thing. It's basically a propeller driven generator which is mounted to an aircraft, and it's for powering some device on the aircraft just by airflow, and the top speed is about 25,000 RPM. The problem is it couldn't be tested to that speed because the wind tunnel didn't provide the airspeed. Target speed is about 420 knots. So what we essentially do, we try to replicate the input into that little device. Just imagine this is the real thing. We also need to measure the torque which goes into it. So what we basically do, we have a motor, which is this one, which is held. I made that already, the footage will come later, which is held here. Basically sits here, so the whole thing can rotate on that bearing, which sits on a mount basically, and we use a load cell which sits down here to measure the torque, the force basically, and with the length we know the torque. As a drive shaft we use a ER11 collet shaft. Don't know which one I'm going to use. I'll probably use the shorter one for the model. The important part on that setup is this area is actually the wall of a climate chamber, because this needs to be cooled down to about minus 55 degrees. So the whole thing should fit into a 1-inch diameter hole into that wall. So this is outside and this is inside, and the wall is basically here. So essentially it's a pretty simple thing. Again, target speed is 25,000 RPM. This motor does 3,700 RPM per volt. So with 12 volt supply we're pretty much there. The motor will be mounted onto that plate. I turned the register already, so it will sit here, and the torque reaction it can rotate here, so the torque reaction will basically pull on that load cell. The only challenge is actually coupling the shaft somehow, because all the couplings I have don't fit here. The shaft is probably about 3 millimeters or so. So what I'm going to do, I'll make a little sleeve and then use either that one or the other one. This one fits to the shaft, so that would be okay. Bearings just go onto the shaft. Get on. So the whole thing sits here. Bearings sitting inside, I probably make a some sort of plastic cap rather than metal, and there will also be a spacer in the middle, which is basically here. This area will be a spacer, which is non-metal, plastic, nylon or whatever, just to keep the distance good. And we also pin it with long pins so it registers properly. So that's the plan, and this thing is going to be finished very soon because I need to demonstrate it. As for electronics, I use a ESC controller and a servo tester, which gives me enough for now. Pretty much the same as I use on my tool post grinder. It's exactly the same setup because I use the same spindle on the tool post grinder, just different bearings because I have because there's more load. So what you do, you use a collet which fits, and then the device and the test can be just fitted here. I don't have the original device. I don't know exactly how it looks like, so all we do is having a stud here, which you can basically just cable tie it, so it doesn't rotate. That's all you need. It's the bearings will center it, and that should be okay. We'll need to check that with the customer. So hope that all makes sense. I was thinking about using one of those, but I think the run out is a bit too much for the speed we have. So let's go for the aluminium one. It's pretty light. This one is made from steel, so it's stainless. It's flexing quite nicely, but it's very heavy, so I don't really like that. The problem with those is the grub screws are here, so we may have a balancing issue as well. We probably need to sort that with some holes. We'll see that. We'll check the vibration anyway. So hope that makes sense so far. I'll show that drawing again, just in case it wasn't clearly visible. So this is our plate with the insulation material in the middle. This is our climatic chamber, which goes down to whatever. The target is -55. This is our drive shaft, which is this. And our drive motor, this motor, sits here. And on this trunnion here, so the motor, the reacting torque of the motor can pivot a shaft or a lever which pushes on that load cell. That's just a shear beam load cell, as you probably would use in a kitchen scale, essentially. I think it's a 2 kilogram load cell, so it should be alright. Alright, let's go on to the machining of that thing. So I already started to make that bushing here, which is basically the carrier for which goes into the bearing. We're just gonna machine that. The problem with this little motor is there is only a tiny little recess here. We need to center that somehow. We need to center it somehow, and I think we're gonna use that recess, but the hole must be big enough, because there is a little ring which rotates. So that's gonna go basically into this way, and we machine some stuff out of here. If we look at the bearing, that's about it. So we got enough meat here. I need to make a shaft extension anyway, because the coupling is too big for that little motor. Well, I mean, it's a little motor. It's 400 watts and 3700 RPM per volt. This thing makes nice and curly chips here. They're pretty sharp. As far as I know, it's EN24. It's just a piece of dyno shaft. Not the super hard one I used last time, but similar stuff. We got about 0.5 millimeters to go. So I'm just doing a spring pass here. Just do a few light cuts. Look at the chips, they are very stringy. Almost there. target is 30 millimeters slip fit. So we got a tiny little bit. You can look at these chips here, nice and blue. Spot on now. That's perfect. So now the bearing should fit. Yeah, feels good. So it's warm now, so let's see the edge. Different tool here. To the corner here. I think that insert is short here. Just found out that the insert was loose, which is a bad thing. See if that works better. Yeah, that's a lot better. So I got an undercut now, I want it.